So today we're going to talk about the unit circle. And really for us, what it comes down to is thinking of an object over here that rotates obviously in a circle. And we're going to consider a point that sits on the edge of that circle. And we're going to apply trigonometry to that point. So for us, it's going to come down to, we're going to build these trigonometric ratios for what we call special angles or certain angles. So obviously a large part of trigonometry is working with angles. We know that so far. Now some angles end up being used much more frequently than others. So for example, 45 degrees happens to be much more important in terms of design and construction. They then say something like 17.34. So because 45 degrees is more important for us, in terms of trigonometry, the sine of 45 and the cosine of 45, they also become more valuable to us as well. So what we would really like, because we're going to use these values a lot, sine 45, cosine 45 for these, these major angles, what we want to try to do is build some precise values, because we live in this world of precision, or we're moving into this world of precision. We want to try to get some precise values for these certain specific ratios. And that's what the unit circle is going to do for us. It's going to allow us to pick off some main angles and get some certain trig ratios precisely, not with decimals. And these special angles, they're all summarized into this theoretical, I guess it's a theoretical tool, but it's this brilliant construction called the unit circle. And that's what it's going to be. So a unit circle has a radius of 1 and is centered at the origin 0, 0 on a Cartesian plane. So here's my middle here, my radius is 1, and as soon as I have that radius of 1, I know right off the bat what these coordinates are. Obviously 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Those are easy to get. What we're going to do is when we overlay a right triangle with a hypotenuse of 1, so the circle has a radius of 1, and the triangle has a hypotenuse of 1, then what happens is the tip of the triangle actually sits on the edge of the circle. It becomes the dot. And that's how we're going to link this together. That's how we're going to link this dot floating around in a circle. We're going to build a perfect triangle that has a hypotenuse, the same radius of the circle. So the upper corner of the triangle actually is the same spot as the dot. So it's pretty cool. Now the next question is, we're going to use this fact, and really what we're going to do is we're going to overlay some certain triangles onto the circle. Now the question is how many? Here, this is an example where they have every possible angle. This is probably going to be thousands or hundreds of triangles. This one, it's a little bit fewer number of triangles. This one's even fewer over here on the right side. There's only, they're going by quarters and so on. So the question is, what's reasonable? We don't want to just break it into a few chunks, but we don't need, 50,000 triangles either. So as it turns out, for the unit circle, we're actually going to build 12. And actually, it's the same 3 triangles, actually 4 times. So there is a lot of repetition with the unit circle, and you're going to see it, and it's going to look very complicated, but once we break it down into some simple structures, it actually becomes very straightforward. So we're going to start with some simple triangles. We're going to deal with an isosceles triangle with an interior angle of 45 degrees. That's probably the easiest place to start, and has a hypotenuse of 1. If we can find the side lengths of the triangle, then we can find actually the coordinate of that corner point, that upper corner point I was talking about. So here's, if I draw a triangle like this, if I can find the length of this side and the length of this side, well, that's going to end up being the coordinate of that point, right? Just like, coordinates and sides of triangles go together. And these coordinates are going to become interesting for us. So let's take a look at a right angle triangle here. Of course, it's going to be right angle for now, 45 degrees and 45 degrees. And what I want to try to find is the value of x. So imagine this is a triangle that's been put inside our unit circle. There's our radius of 1 right there. And I've opened this thing up 45 degrees. Sure. So this is going to fit inside a unit circle because I have that radius 1. So the question is, well, what are the lengths of this side and this side? Because if I know this length and if I know that length, I will then know the coordinate. I'll know the values up there. Right? Remember, this is the origin, right? This is down here at 0, 0. So however far over I go along here is the first coordinate, and however high I go up here is the second coordinate, just like we plot points. So in this case, let's try to figure out x and x. It happens to be the same. Well, we can use Pythagorean theorem. I know x squared plus x squared equals 1. X squared plus x squared is 1, just from Pythagorean theorem. 1 squared, sorry. So I can solve this. X squared plus x squared is 2x squared. Obviously, we know 1 squared is 1. I'm going to divide both sides by 2, and I'm going to square root both sides. I'll take the positive value because we're not going to have a negative length here, so I'll just take the positive 1 over root 2. Now, if you put that into your calculator, you're going to get around 707-ish, okay, which is fine. That's the long decimal value that we're trying to avoid. I mean, we know what that number is, but we're not really going to use that number. We really want to use this exact ratio, 1 over root 2. So, because 1 over root 2 is the precise value. This 0.707-ish is kind of rounded off. Okay, so that's where this 1 over root 2 comes from, and that represents this length there and that length there. Now, just notation-wise, and some textbooks are different. For notation, some textbooks don't like this radical down in the bottom. So what we do is we just multiply the top and the bottom by root 2, because we know root 2 over root 2 is 1. If I have root 2 over root 2, they divide out and it's equal to 1. So I'm just multiplying this thing by 1, which I'm allowed to do. But when I do that, I get 1 times root 2, which is root 2, and I get root 2 times root 2, which is 2. So the point is this is exactly the same as that. It's the same thing. If you put this into your calculator, root 2 over 2, you get the same thing, 707, whatever, whatever it is. It's just this doesn't have the radical down in the denominator. It's just a notation thing. That's all it is. It's kind of like, it's like reducing fractions. If you ever had 5 over 10, that's the same thing as a half. And, we could leave it, I guess in theory, we could leave it 5 over 10, but, notation-wise, we always reduce it. It's the same idea here. So just to kind of match the textbook and match some of the questions we're going to see, a lot of them use this root 2 over 2, which is exactly the same as 1 over root 2, which is always, of course, is 707. Anyway, so it's a better form for us to look at. So I'm really just going to rewrite this 1 over root 2, this x equals 1 over root 2. I'm just going to write it as root 2 over 2. It's still the same thing. It's still 707. It's still that exact number, just written a little bit differently. Now what we're going to do is we're going to examine SOHCAHTOA and notice actually a very interesting overlap. So here's back to my triangle. I know this distance. I just worked out x. X was root 2 over 2. I just worked it out. X was root 2 over 2. I just worked it out. I have 45 degrees here. I'm going to write sine of 45. I'm going to now apply a trig ratio to this triangle that we put into this circle. Okay, so we sort of have the third level here. Okay, sine 45, I know from SOHCAHTOA, is opposite, okay, over hypotenuse. Easy. So I know the opposite, root 2 over 2, and I know the hypotenuse is 1. Got it. Now this is actually super important. This is the great advantage of having 1 as our hypotenuse, because we know, okay, sine 45 is opposite over hypotenuse. So it's root 2 over 2 over 1. But having something divided by 1 doesn't change anything. So we don't need to write this divide by 1. So what that means is we can write sine 45 as root 2 over 2. It is over 1, but I'm just going to drop it off. I don't need to write it in because dividing by 1 doesn't matter. And that is actually really, really important, okay? So if you go to your calculator, okay, I want you to go to your calculator right now, make sure you're in degrees, and type in sine 45, you're going to get this number, 7.707-ish, and so on. But from now on, we're not going to use our calculator. We're going to use root 2 over 2. If you type in your calculator root 2 over 2, it's also this same thing, 707. So it's actually pretty cool. So what we've done is we've been able to, as we're constructing this unit circle, we actually have the precise trigonometric value for the sine of 45 degrees. It's perfectly root 2 over 2, which is actually good news for us. Likewise, it's the exact same structure. We won't go through it. It's the same structure for cosine. On your calculator, if you type in cos 45, take a second to try it. Cosine 45. It's root 2 over 2. Same thing, because we know cosine is adjacent over hypotenuse. And this, root 2 over 2 over 1 is root 2 over 2. So it's actually pretty cool how it goes. So we notice these two trig ratios end up being just the horizontal and vertical lengths of the sides, right? This is the sine 45 is root 2 over 2 and cos 45 is root 2 over 2. So what that means is that if I start here at my origin, 0, 0, I go right, 0.707, which is the same as root 2 over 2 over 1, which is the same as cos 45. And the same idea here, which is sine 45. So it's actually pretty cool. So the point here is the upper coordinate, because this triangle is radius 1, or hypotenuse 1, the coordinate of this point that's moving around, this big circle, is actually cos 45 is the horizontal and sine 45 is the vertical. That's how we tie trig into circles. That's what we're doing. We're trying to have trig and circles go together. And that's what really this next topic in trigonometry is. It's taking all our rules for triangles and applying them all to circles. So I'm going to summarize this. We'll go back to our circle, radius 1. Here's my root 2 over 2 here. My root 2 over 2 is there. I'm just going to put them now. We just write them again just form-wise for the unit circle. I'm going to write them as coordinates up here. So I have this coordinate, right? Typically, here's my origin, 0, 0. I go right and up. So I go right root 2 over 2 and up root 2 over 2. So if you want to start, you can start, you're going to have to draw a unit circle. You may want to start constructing it on a page. But the point is, the first coordinate on our unit circle, the first coordinate is the cosine of this angle of the opening. And the second coordinate is the sine value of that opening. That's how this all gets put together. Because the first coordinate here was over, and the second coordinate is the up. The first one is cosine, second one is sine. So that actually works really well. And we can keep going with this. We know this coordinate down here was 1, 0. So this is 0 degrees. So try on your calculator. On your calculator, go cosine of 0. You should get 1. And try on your calculator, go sine of 0. You should get 0, which is pretty cool. And we have this coordinate up here. That's 0, 1. This is 90 degrees, right? If I opened it up all the way there, that's my triangle. That would be a 90 degrees. 90. So on your calculator again, go cos of 90. Cos of 90, you should get 0. And if you go sine of 90, you should get 1. Okay, it's actually pretty fascinating how it all goes together. I know it's theoretical, but how it all gets constructed is it's pretty incredible. So we can actually now keep going for all of the angles in 45 degrees. Don't worry about radians yet. We'll talk about radians later. So for 45 degrees. So this here, because really this triangle is really the same as that triangle. It's just the signs are different. It's just, this is a positive distance and a positive distance. This, we go negative in this direction and positive, but we know, we've seen from property of sines before, those distances are the same. That distance there is that distance. So it's the same triangle, it's just flipped over. So we don't have to go through this whole process for all these triangles. We just need it for the first one, just this triangle here, and then we just flip it to there, flip it down there, and flip it over there. So these coordinates now, they're the same actual numbers. It's just the signs change, right? Here they're both positive. This one, the first coordinate's negative, the second one's positive. Here both coordinates are negative, right, because we're left and down. And here the second one's negative because we're right and down. But the numbers are exactly the same. So now we have the sine and cosine ratio, not just for 45 degrees. We also have the precise values for 135, for 225, and for 315 as well. Plus, we already know these ones are easy, 1, 0, 0, 1, and so on. So we're starting to construct this circle. Now, one more triangle. We can't, the unit circle isn't just about 45-degree triangles. We want to use 60-degree triangles as well. So I'm going to build an equilateral triangle, 60, 60, 60, okay? I'm going to make the length of one side 1. It has to be 1 again, so it fits on my unit circle. So what that means is I'm going to put this coordinate, this corner down here at the origin, and this point up here is going to be sitting on my circle again, right? Because that's a length of 1. That's my radius of my circle. So that's at the origin. This is sitting on the edge of the circle. I have my opening here, 60 degrees. Okay, so it's not 45. We're now talking about 60. And what I'm going to do is I like the world of right triangles. So I'm just going to cut this triangle in half. And I want to be able to use SOHCAHTOA. So when I do that, this 60 up here becomes 30. Okay. And because this was equilateral, that was 1, that was 1. This whole bottom was 1. Okay, now my whole bottom is a half. So I just cut my 1 in half. So now my right triangle I can deal with is this one here. Okay, so what I'm going to do, by Pythagorean theorem, I want to try to figure out what y is. I know my hypotenuse is 1. I know my base is a half. Got it? But I don't know what y is. So Pythagorean theorem, I know y squared plus a half squared is 1 squared. Y squared plus a half squared is 1 squared. I know a half squared is a quarter. I know 1 squared is 1. I'm going to just subtract a quarter from both sides. I'm going to find a common denominator. Obviously 1 is 4 over 4. 4 over 4, take away 1 over 4 is obviously 3 over 4. And then I'm going to square root both sides to solve for y. Square root the top, square root of 3, I don't know. Square root of 4, I do know, is 2. So I know my y is root 3 over 2. So that my height here, my y, is root 3 over 2. Okay. Now what I'm going to do is I'm going to try the sine ratio. I'm going to use sine 60 is opposite over hypotenuse. Okay, sine 60, opposite over hypotenuse. I'm going to go, okay, sine 60, opposite is root 3 over 2, hypotenuse is 1, got it? And we have this great advantage again that pops up of using this 1, is that root 3 over 2 over 1 is the same thing as root 3 over 2. So now I've got it again. There's my exact ratio for sine of 60 coming from this triangle. I want you to try on your calculator. On your calculator, I want you to type in root 3 over 2, see what you get. And you're going to get 0.866-ish. And I want you to type in sine 60. You're also going to get 0.866, exactly the same. Okay, so this is the exact ratio for a 60-degree angle for sine. Okay, do the same process. It's the same thing for cosine. Cosine is adjacent over hypotenuse. So a half over 1 is just a half. So a half, of course, we know is 0.5. So go on your calculator, go cos of 60, and you'll get 0.5. So here's my 60-degree triangle, my 60-degree opening. First coordinate's a half, the second coordinate is root 3 over 2. Cosine and sine, same structure. Now I can flip it. We're not going to build all the triangles again because a 60-30 triangle is the same thing as a 30-60 triangle, just flipped around. So I'm just going to have this triangle flipped, which means I just need to flip the coordinates on the end. That's all. So putting this all together, this is what we're looking at so far. If we have just the upper right corner, because you're probably saying this is super confusing, but this actually gets really simplified very quickly. We have the upper right corner, okay, of the unit circle. Here's my 0, there's my 90. Okay, 30 degrees, 45, and 60. These are the only angles we're going to build it with. Okay, the unit circle, we don't do it for 17 degrees. We don't do it for whatever, 63 degrees, those oddball degrees. No, we just build it for these main degrees, 0, 30, 45, 60, and 90, because these degrees pop up a lot when we do calculations. So when you see, the 1, 0 is pretty easy to write, and the 0, 1 is easy to write. And then you see all the fractions are actually all divided by 2. Okay, so every coordinate is divided by 2. Got it. And then you see the numerators are all roots. Okay, and then we say, okay, well look, I'm just going to start here and go 1. Now this is root 1, which is the same thing as 1. So it's, you don't have to put the root in, but just for the pattern. So it's root 1, root 2, root 3, and then root 1, root 2, root 3. And that gives you the structure. It's pretty impressive, eh? How it all goes together, how it all connects. It's actually very interesting. So for us here, this is what it's going to look like. I'm just going to drop the radicals, but these are the structures we're going to use. And now what we can do is we can imagine this dot. It doesn't just sit in the first quadrant. It actually rotates around a circle. So any multiple of 30 or 45 or 60 that sits over here on these sides, it's the same values, it's just different signs. That's it. So these actually, these two triangles, this 45-degree triangle and that 60 that got flipped to 30, allow us to build all these essentially coordinates all the way around the outside of the circle, of the unit circle. And again, it's just for these special angles. And that's where the 12 triangles come from. There's 3 here, 3 here, 3 here, and 3 there. Those are the 12 triangles that we have within this circle. Now, in summary, this is all labeled, all put together. So you can make a note of this. You know, if you have a printer at home, you can print one of these off. You do want to have a unit circle for yourself as a tool to help you use and solve problems. And the key, remember, the key with this is that we use it to be exact. Okay, we use the unit circle to give us exact values. Okay, take a look at page 229.